So today I will continue talking about the open flow channel. I know that there's a little bit of the lamina and turbulent that is not finished, and some other of the other part that is not finished as well. So I just want to finish the open channel flow as fast as possible so that I can go back to lamina and turbulent flow. Okay, so now I want to go through the summary for a bit, and then I can go to the exercise that is waiting for us, because this is like kind of related to what we learned not last week, this week. Okay, so now we have uh the, the overview picture of what we have learned is about the non-uniform flow for this week, because we already learned about the uniform flow last week already. So uniform flow is basically the y here, the height here is always the same, which is the normal depth here is always the same. But for the non-uniform flow, the depth here is quite different. By different, I mean that it's quite going, like this is shorter and this is like upper here, because the flow is not flowing uniformly and it's not that straight line, or I mean the straight slope. Yeah, so in non-uniform flow we have the mass conservation is added, because in the uniform flow there's no acceleration in the flow, which makes that there's no force, and if there's no force there's no mass conservation equation as well. So there's only two equations, or two factors that we're going to consider for the uniform flow, whereas in non-uniform flow we have to also consider about the mass conservation as well. So for the critical slope, I think this one we have done some exercise, so I guess you guys have understood this one. Fruit number less than 1, it is the subcritical flow, and if the fruit number is more than, oh no, not more, yeah, more than 1 is supercritical flow, and if it's equal to 1, it is critical flow. Okay, and this is the formula that I don't think we have to use it yet, but as soon as possible, we're going to use this one. But well, last week, I mean this week lecture, the professor didn't tell us anything that we have to, like consider, or trying to, like, in the example, like there's only in the exercise, or what do we call that? There's only like the concept that we're trying to study this week. So yeah, then we have this one, which is like a dam. Yeah, and the flow is like this. So of course in a dam there's like the sand and gravel that cause erosion, and it flows like this to the river, right? So when there's the river, it creates the subcritical flow. It creates a condition that allows the subcritical flow, and there would be another hydraulic jump over here. So hydraulic jump is like when there's the depth is like quite low, and then like it jumps to a huge depth here, like a really long depth here, so it creates some turbulence here or something like that. So it creates the height is about 4 to 6 times of the height or of the depth of the water. So when supercritical changes to subcritical, it creates the hydraulic jump. As for this one, as you can see, normally the river is something like this, right? So when the river is something like this, there is it creates the angle here. So angle here creates the slope as O here. So when it creates the slope, the length here, or the depth here, because as in nominal depth, I mean normal depth. If this one is the same like this, so this must be the same everywhere, right? But in this case, it's not the same, because it creates some sign of slope here. So it creates y like this, but we have to plus this one. So this here is equal to this here, but you have to plus this one, right? So it creates this formula, y plus s0 x1, whereas x1 is here. Sorry, x1 is here, and this is the y here. So if you want to find this one, you choose this one and plus with this one. So this is the energy equation, and then we can get the delta energy over delta x, and this is what we get after we cancelling out this and this, we cancel out, so we have S0 that is next. So HCl is like the hydraulic grade line that connects from here to here to here. So basically in the pipe our pipe, or actually a water source, but we cannot see the surface of the water, right? We cannot actually go like, okay, this is a water at the pond and we're going to put the something to measure the height or the depth of the water on the surface. It's almost impossible to do it. So if there's a pipe like this, they're going to put a hole inside this one and create it in the manometer, and then we can see the hydraulic grade line. So for the energy grade line is the main factors are the velocity and the pressure. So it's sometimes going to be like this, or like there are two lines in the pipe work. It's the hydraulic grade line that measures the water, and the energy grade line that measures the energy, right? Okay, so now we are going to the this graph. It is there. We won't appear on the exam, I guess. I hope so. But when we work, if we're going to work in something related to pipe and like designing the gutters or something like that, I guess we need to study about this one and understand it. So I'll just go to it quickly. We have five types of flow, and is it types of flow? Yeah, the five type of slope, and 12 solution to these five. So it says solution, the solution means the curves here. So we have S1, S2, S3 for the steep slope, and we have C1 and C3, which is like for the critical. So S stands for steep, C stands for critical, M stands for mild, H stands for horizontal, A stands for adverse. So why are these numbers like 1, 2, 3, or sometimes just only 2, right? But why is it 1 and 3, but this one is 2 and 3? Because this is the regions that are going to break apart between each line. So for region number 1, it's a space between the topmost line. So as you can see that for number M1 is going up like this, it's going up here and it's going up here. So it's like the topmost line here. It is the space between there, right? But for the space between top line and the next level is the region number 2. So the top line here, they mean this one, right? And to the next level line. So this is like trying to go down here. So this is have 2 here. But this one, where is number 2? Because this is going up like this. It's not trying to come down to this lower space here. You see that it's not trying to come down to the lower space, but it tries to go up here to the space. It works the same for this one. Even if it's like this, it's not coming like this, but it's going this way, but still it's coming down to the lower part here. And there's number 2 is coming to the lower part here. It's not trying to go up here, it's not trying to go up, but it's trying to go down here and down here. And for number 3, it's the space between the second line and the bed. So why does this one and this one is like going up? Why it's not A1? Because it's trying to link with the bed. Yeah, so that is all for what we have learned, and this is some kinds of limits and derivative of the answer, but I think we can just go through it quickly. So if y is going to is approaching y0, of course the velocity is going to be velocity 0, the initial velocity, and the slope is also going to be the same. So if we derivative it, this one is equal each other, right? So it is 0 and 0, because the formula is like this, s0 minus s over 1 minus fr squared, but this one is already s0. So that's the reason it's already 0. I'm trying to talk as fast as possible so that we can go to the example quickly. And for this one, it's also the same. But if the lower part here is 0, so we get alpha infinity. But if the top part here is 0, so it's 0. And for S0 over 1 because FR is already 0, so 1 minus 0 is 1, so we get S0. So that's what comes for this one, and this is like some simple things that you can understand on your own, right? So I'll send this to you guys already, so you can just check it. Now let's move on to our exercise. Okay, so let's read the exercise together. I think this one is quite easy because they're only asking for 2 questions, whereas the other questions are like asking for 3 questions or 4 questions, like A, B, C, D. So this one is only A and B, but yeah, it's upstream and downstream. Okay, so for the discharge here, of course they're asking for the Q, Q here, and the fruit number is just FR. So now let's highlight all the numbers that we're going to use. This list gate controls the flow in the channel of a width 2.5 meters, and if the depth of water upstream and downstream are 1.4 and 0.2, I guess it's something like this. As the effluent, upstream is like going down here. I don't want to draw this one, I'm not really good at drawing. The sluice gate is going to be like this, right? And the water is going down, flowing down here. So this is like 1.4 and this is 0.25. Yeah, just like that. Just imagine that it's like flowing from the upper part here and going down part here. Okay, so now, let's start with A. We're finding the discharge rate. So on the either side of the gate, we have this kind of equation, which is the total head equation. So Z(S1), which is the datum head of datum, U1 square, which is the velocity. Oh guys, I just found out that GoodNotes already gave us like a really nice feature. Maybe I just discovered it out, but it's kind of nice. It's like the sticker function for us to decorate our notes. Okay, let's go back. Let's go back here to G. I think you guys have seen this plenty of times. Like, you don't need to like know where the equation is from because this is a common equation in hydraulics. CS2 plus, because the other side of the gate, so we're trying to do the upstream side and the downstream side of the gate. Oh no, not the upstream and downstream. What do we say? Because the gate, there's 2 sides of the gate, right? So of course we need to consider both sides of the gates to G. So we have H1 plus Q, and this will be square as well, and over 2G, another H1 square, another H1 square. Okay, so this is like, it comes from this one, H2 plus Q square over 2G H2 square. So we can move this one here and this one here. So we get H1 minus H2 equals to Q squared, because the Q is like a constant, almost the same. Sorry for my bad handwriting of Q. It's supposed to be something like this. Yeah, a little cute one. 1 over H2 squared, because this one is here, right? So it is the one that is moving, so it must be minus H1 squared. Minus 1 over H1 squared. This is everything here, and another everything here, and everything here. Okay. Okay, then we can continue to wait, why should I continue? substituting all the values that we have. Okay, so now we have 1.4 minus 0.25 is 1.45. Okay, I'll just write it. 1.4 minus 0.25 equal to G, no, not G, Q square over 2 times 9.81 over 1. This one's supposed to be 0.25 square minus 1 over 1.4 square. This is another bracket here, so you won't be confused, like where should we minus and where should we multiply it, right? So now we have everything that we want. It's 1.15 meter here, and this one is, oh wait, 1 over 2 times 9.81, and this is time the whole thing here, 1 over 0.25 square minus 1 over 1.4 square, and this is bracket 0.7895. 0.7895 q square. So now we can find the flow per unit of the width of the gate. So q here equals to 1.15 over 7395. Okay, and then q equals to the square root of, okay, I want this one to be up over here, 1.15 divided by answer, it's 1.456. Square root of 1.456 is 1.206997, right? Meter cubic per second. So this is the answer for the flow per unit, but we are trying to find the total discharge. So the total discharge here is Q equals to Q, the little q, times with the gate, the width of the gate. Yeah, the width of the gate equals to 1.207 times 2.5 equals to 3.017 cubic meter per second. Okay, so this is per unit width only, but this one is the total one. This is the total. This is only per unit. So now we've finished with question 1 and we're continuing to question B. So the question B, they're asking for the fruit number, right? So for the fruit number, basically it's a rectangular channel, right? The sluice gate is a rectangular channel. So FR, I hope you guys remember the FR formula by now. GH. Why is it not working again? Okay, it's working. GH. So GH here is U equals to Q O H. Okay, so we can say that this one is Q. Please note that this is the smaller q, because if it's a larger q, it's going to be q over a, right? So this is just only this molecule. Square root of DH3 power 3. So now we can write it this way. It's going to be divided into two parts here. The first part will be the upstream. So this is the upstream. How do you know if it's the upstream or the downstream? The upstream is always a higher number. Is it? Is it always? I'm just trying to think. I don't think it's always, but you can, it's given the first one from upstream to downstream, so you know that the first number that they give you is the value that you need to use for the upstream equation. So this is 9.81 times 1.4, which is the height. The answer is 0.2326 is 3. Okay. 3, right? And we also have, let's do it this way. Downstream here. FR2 is the same, 1.207. Overall, this one is 0.25 cube because it's the downstream depth here. Some people say it's depth, some people say it's height, so it's basically the same thing. Answer is answer is 3.08. 3 meter. This is also in meter. No. Fruit number doesn't have any meter. Sorry. Okay, so now we can finally finish this one very quickly by only 10 minutes. We broke the record, yay! But this one is actually an easy one. So yeah, it's also quite short. I'm trying to make it look a little bit long and complicated, but yeah, it's very simple to. It's impossible for us to make it look complicated because the question is too simple. Okay, so now we can move on to the water passes a sluice gate. Water passing the sluice gate in the horizontal channel a width of 2 meter, and the depth of the flow is there's two sides, 1.8 and 2. So normally the gates they have two different depths, and the hydraulic jump occurred is then of the downstream. So finally we're having the hydraulic jump that we have learned here. Where is it? Here, the hydraulic jump. The water is trying to jump. Yeah, right. Okay, so now we need to find the force that is on the gate. Why do we need to find the force? Because as you can see that in the uniform flow, there's no acceleration, no force. But in this one, there's this one is 0.3 and this one is 1.8. So it starts to have some kind of acceleration that creates the mass conservation equation that's going to happen here. Then we need to find the depth of the flow downstream of the hydraulic jump, and then the fraction of fluid energy that is dissipated in the jump. Okay. Oh, there's another one. Ooh. Nice one. This one is quite long here. Let's just finish this one first. I'm gonna use this page because I already added. As if I'm using kind of real page that I don't want to waste. Okay, so now let's find part A. We're trying to find the force on a gate, so we need to use the momentum principle, right? So that are given. Velocity will be found by the flow rate. So first of all, we need to just do the same thing as above one here. Total head. I think this one is going to be a bit long, a little bit long. Okay, so now we have CS1. It's just basically the same as the previous one because it's the sluice gate the same. So same concept, same stuff, just we're asking for different parameters. S2 plus U2 squared over 2G. Yeah, right, I'm right. So then we can continue to this one, which is H1 plus, am I being too loud? No, right. Okay, so this is 2, the same, G. This will be H1 squared. Okay, and this will be H2 plus Q squared to G. Okay, so H1 minus H2 goes to Q squared over to G times 1 over H2 squared minus 1 over H1 squared. Okay, so this is all done. Not yet done. And then we can find, what else can we find from this one? We substitute things here, right? So H1 equals to 1.8 meter and H2 is 0.3 meters. So then we can finally substitute everything in. 1.8 minus 0.3 equals to 222 Q squared over 2 times 9.81 1 over 0.3 actually. It's H2 squared, okay, minus 1 over 1.8 squared. Okay, so this is all for today. Just kidding. I just miss hearing this word. Okay, so I don't need the calculator here, right? So 1.5 meter equals to Q squared. Wait, I think I can do it better than this one. Not do it better. Compute it and write it better. In the better form. 1 over 0.3. Can you still hear my nozzles? Not nozzle. Yeah, I'm not really well yet. So 0.55. Okay, so this will be 1.5 divided by 0.55. Answer is 2.727. So I square root this, and I delete this, and I get the answer of this one. 1.651 cubic meter per second. So the same thing here, it's the flow per unit width, but we're trying to find the velocity rate. So u equals to q which is equal to 1.651 h1. H1 is 1.8. Answer is 0.917 meter per second. So U2 is also the same, Q is the same, H2 equals to 1.651 over 0.3 equals to 5.503 meter per second. So these are the velocity for the corresponding height, depth. So if F is the force that is exerted on the gate, so the momentum principle of it. Of course, there's the formula for finding this one. So it's 1 over 2 rho g. I hope you remember this formula, right? 1 over 2 h22. I mean h2 squared. I'm already used to saying h22, h12 is, you know what I mean, right? It's going to be the upper part here. And rho g b u2 minus u1 plus f. So f here, we are going to rearrange everything here. I should have had it aligned lower. 2 here, rho g b h1 minus h2 and then we minus because this part here is going to be here. Rho g b u2 minus u1. So I think we can substitute everything here. It's 1 over 2. For the rho, it's for water, so water is 1,000 times 9.81 times the base. Basically the base is 2. Width of it is 2 meter. Times 2 times 1.8 square minus 0.3 square minus 1,000 times. You can also factor it out. It's faster than what I'm doing now. U2 is 5.503 minus here U2, and this is U1, so it's 0.917. The answer is 1 over 2 times 1,000 times 9. Okay, so the answer is 157. No. 15.7 kilo Newton. 1, 2, 3, 4. Yes. Wait a second. Yes. Okay, so then we can see the conditions. We're going to the second question that, oh wait, I should do this. Yep. Huh? Okay. Am I on the right page? Yeah. So the depth of the flow downstream of the hydraulic jump. What are they trying to ask? They're trying to ask for the depth, right? So if we're trying to find the depth, of course we need the fruit number. It's very important. So for the fruit number here, we're going to use the same formula. I think you guys are already sick of the formula that we're going to use. It's the same formula always, but you know, practice makes perfect. GH. Okay, so now we're trying to find the downstream. So let's say downstream is D here, D here, D here. Okay, so we have 5.503 over, this would be a very long thing here. G will always be the same. 9.81 times with HD, H of downstream. The depth of downstream is, calculator, square root of 9.81 times 0.3 equal to 3.207. Foot number is in the unit. So we can find the hydraulic jump relation. So jump. The hydraulic jump here we have HB equals to HD over 2, the downstream, alright? And times with minus 1 plus, there you go again, it's supposed to be really long here, plus 1 plus 8 fruit number square, but this fruit number is the fruit number of D, okay, and this is in the square root, so everything here is going to be like this. Okay, and then now we can find this one that we got earlier. It's 0.3 over 2 times minus 1 plus 1 plus 8 times 3.207 square. This would be the bigger bracket, because we already used the round bracket already. So now let's compute this together. 0.3 over 2 times 1.2188, 1.219 meter. So this is the downstream depth of the jump. Okay, then we can continue to the last question. I think we're doing quite well these days. We're going so quick now. So the next question that we're going to solve is the fraction of the fluid energy. Fraction of fluid energy that is dissipated in the jump. So basically, we have another, not really a new formula, but yeah, it's a formula that you guys have already seen previously. Okay, so now for letter C, question C, we're going to find the velocity downstream of the jump. UD is equal to Q Why are we using HB? Because HB is, they said, the velocity of the jump. Okay, here, jump. So we're using the jump. We're using the HB jump. And then it is equal to 1.651 here, or 1.219 equal to 1.354 meter per second. And then we can see the total heads on the either of the jump. So it's basically kind of, what do we call that? Height? Something? Yep. Okay, so now we have 1 HA equals to Z plus UA squared. This is supposed to be A2, right? Yeah. ZSA, and this is 2G, and then we plus 0.3 plus 5. Can you remember this one? It's from this part here. This part. But later we're not going to use this one because we're going to use the new number that we just found here, 1.354. So this one is over to G, and the answer is okay, 1.84342 HB equals to ZB plus UB squared, everything here over to G equals to the previous one that we found. It's here, 1.219 plus 1.354 square, or the same thing here, 2 times the gravity, 9.81. Answer 1.312. Yep, this is meter because it's a head. So now the fraction, they're asking for the fraction, right? The fraction, they're not asking for each head. So the fraction here will be delta H over H HA. Why is it HA? Because they're asking the fraction of the fluid energy that is lost, right? I don't like this line. Okay, so now we have 1.843 minus 1.312. Everything here equals to 1.848 like this, and the answer is 0.2881. So it's probably times 100, probably 28. So if they're asking for a diffraction, it's basically they're asking for the percentage of the energy that is lost. Okay, so now we have quite 16 more minutes. I hope we can continue to the next question. Let me see. Give me 3 seconds to let me read the next question here. You can also read with me. Okay, so I will skip this one. It's quite long, so I don't think that fits for 15 minutes. So I'll just go to this one. This undershot sluice control. Yeah. Okay, so now, is it really short? I'm starting to wonder if it's really short. Okay, so this undershot sluice controls the flow channel of the width 1.5 meter. So if the flow rate is 3 meter per cubic meter per second and the upstream depth is 1.8, so the width here is 1.5, the flow rate is 3.3 cms, and upstream depth is 1.8 meter. So they ask us to calculate the minimum depth and the fluid number. So the downstream, okay, so we need to find two things with two conditions. So the first condition they're giving us is no energy loss, and the second condition is a 10%, so like the fraction, the H over HA in the specific energy through the sluice gate. So let me add the square paper, and I'll move this question after the square paper, so next time we can continue to that the rectangular channel. Something, yeah. I see something we need to use the Manning equation again, so I'll just skip it one. So let's start with this one first. The specific energy, so we always need to use the specific energy as, I'm sorry for the noise in the background. Some people in my building does not. Sorry. My apologies. So the specific energy is, we're finding the specific energy equation now. So E is the symbol of it, so plus with U squared over 2G. So the answer is, not the answer, I mean we expand it to get quite a lot more things that we know, because we don't know this one. We don't know this one. Oh, we know this one, but we don't know this one. So we're trying to substitute anything as many as possible, as many as we could. So this is just for information. It's still the rectangular channel. So with they gave us the Q, right? So the Q here is 3 cubic meter per second. So now we can get E equals to H plus 3 cubic meter per second square the lower part here is 2981 times b is 1.5 square times h square. So we don't know the h here because we're trying to find the h. And the e, that is, just leave it here. So the answer is, for only the number 1.5 square. Okay, so this is h plus 0.2038 over h squared. Right, so now we have everything. This will be the upstream, because upstream they're giving us upstream they're giving us 1.8 meter, right? So plus with 0.2038 over 1.8 square, and the answer is plus 0.2088 over 1.8 square, 1.8629, let's say 3 meter. And for the downstream here, downstream we don't know yet because we're trying to control the flow, right? So super critical, h plus 0.23 hd squared. Okay, so now we need to find the solution of it, which we need to find E, right? So of course this is equal to E2. Yeah, this is the E1 here, E2 here. Okay, so then we have to find this part. Then we can find the condition that they're going to give us. So A, this is not the A actually. A here, we're trying to find the condition that they gave us. No energy loss. So if it's a no energy loss, which means that E1 equals to E2. E1 is equal to E2 equals to 1.863 meter. So you can easily find the, yeah, we can easily find this one. So HD plus 0.2038 over wait a second, I'm going to use a solver again, so it will take quite a while for me to click. Yeah, if you guys know what I'm talking about. I always need long time for the solver function. Ouch. Okay, please wait a second. Oh, I think I made a mistake, sorry. I need to do this one first. Oh yeah, square here. You guys are so smart. Equals to the square root of, because this is the h here. CO2. But this part, I'm going to pick this one as 0. So I don't need to use the solver anymore. It's 305 over 1.863. Okay, the answer is 0.3307 meter. Okay, so then we can find the u, which is the velocity. Okay, so the u here equals to q over a q over bh, and everything here equals to 3 over 0.07 times with the base 1.5, and the velocity here that we get is 6.047 meter per second. So then we can find the fruit number equals to u over this part here. Yep. I know that G is always that one. 6.047 over. What's happening? Okay. The answer is 9.81 times h, which is 0.3307. Answer is 3.3572. Yeah, this is the fruit number. So then we can continue for so this is the answer, but this one is the answer. Okay, so for B it is very simple, it's the same, but for B there's 10% in specific energy loss. So B E2 equals to 0.1 minus 0.1 of E1. So it's 0.9 of E1, which is 0.9 times 1.863. 1.86. Okay, it's equal to 1.6767 meter. So we need to do the same, because if h0 equals to 0, h would be square root of 0.209 over 1.677. Answer is, wait a second. Wait a second, I'm trying to use the solving equation. Okay, so it's 0.3999. Okay, 5 meter. So then we can okay, so if you guys wonder where it's from this part here. Okay, it's from this part here. So we have this one, and we can continue to find the u, which is Q over BH equals to 3 over 1.5 times 0.3995. So 3 over 1.5 times 0.3995. Answer is 5.006. Answer is in meter square per second. Oh, not meter square, meter per second. So then we can find the fruit number, which is the last thing that we're going to find now. And the same thing here. Square root of GH equals to 5.006 over 9.81 times 0.3995. Answer is 2.529. Eight, 7 is 9. Okay, so this is the fruit number without any unit. So first of all, if no energy loss, the answer would be 0.33. What is this? I forgot it. E2 equals to 0. Oh, not E, H. 3307 meter. Fruit number equals to 3.3572. And if there is 10% in energy loss, H2 equals to 0.3995 meter, and fruit number equals to 2.529. Okay, so this is the final answer. Okay, so that's all for today. We have done 3 questions so far. The first question is about sluice gate. Second question is also about a sluice gate, and the third question is also about the sluice gate. And then we are going to work on another sluice gate later. Then we finally get out of the sluice gate and try to calculate the drainage area, which is something similar to this one, if you can remember. Yeah, this one here. I try to find the things that's going to be similar to this kind of like a rain, and then what happens if the rain keeps coming and there's like no gutter or something. So this kind of exercise is quite the same, and it will also be the similar here. I think this take quite a longer time. Okay, so that's all for today. Thank you for listening. If there's any question, please feel free to ask me anytime. Thank you. Bye bye.